In this video, we're going to cover what linearizations or linear approximations are, how to use them, the formula that you can use to find them, and a special trick so that you don't have to remember that extra formula. Let's jump in. So first, let's start off with what a linear approximation is. A linear approximation is a linear equation that approximates another function that is nonlinear, around a certain value, I should say. So specifically, if this is our value, this slider here, let's set it equal to 1, for example. If I want to approximate this actual function, sine of x, around that value, basically what a linear approximation is saying is that you can just pretend like sine of x is a linear equation around that value. Now, it's obviously not a linear equation, right? It's not a straight line. However, here's the trick. If we zoom in 100 times or 1,000 times or 1,000,000 times, if we just keep zooming in forever, then it's going to look more and more linear as we zoom in. And this is true of any function that is differentiable at a certain point. Like if it's not differentiable, this would not apply. It would look like a sharp corner still if you zoom in infinitely far. But if it is differentiable, if the derivative exists, basically there are going to be no sharp corners. So if you zoom in 1,000 times or 1,000,000 times, you'll always be able to do this. You'll always be able to zoom in far enough that the function that you're dealing with, even if it's not a linear function or a linear equation, it will look like it is a linear equation if you zoom in far enough. And that's kind of the idea. Another way you can think about it is, the surface of the Earth is spherical or approximately spherical, but if you stand on the surface of the Earth, it looks flat. You don't really see the curvature. Why is that? It's because you're zoomed in extremely far to the surface of the Earth. It's a similar kind of idea with this. If you have any curve and you zoom in far enough, it's basically going to, as long as there aren't any sharp corners, it's basically going to look like a straight line if you zoom in far enough. And that's essentially what we're taking advantage of here. So basically, we can pretend like this function is a linear equation as we zoom out. Obviously, as we zoom out, it's going to look less and less, or it's going to look more like the original one, less and less like a straight line. But that green line, that is what we can pretend that the function is at that value. Because again, as we zoom in really, really far, the red and the green line are essentially indistinguishable from each other as we zoom in. So if we just pretend like we're dealing with the green line, we can use it to calculate certain values. And again, it won't be perfect, but it'll be almost perfect, or it'll be so close to perfect that it's good enough. Even if the red function, the original function, is not actually a linear equation. So there you go. That green line, this green line here, this is the linear approximation of the function sine of x around the point x equals 1. So whenever we have a setup like this with some function f of x that is curved in general, and we have a certain point that we want to approximate the function around, we can always come up, assuming it's differentiable, of course, we can always come up with a linearization, this straight line that acts as a linear approximation to the function around a certain point. Now the question is, how do we do that? Basically this formula. So this formula here, essentially what does this represent? At A is essentially your x value, the point that you're approximating around. F prime, obviously the derivative of the original function, and then x minus a plus f of a, that's the y value of the original function. So if you're dealing with the linearization equation and you're trying to find linearizations, you can literally just do that with this equation. You can always plug it in, assuming you know the function and the point you want to approximate it around. However, there is, in my opinion, a better way to do this. I actually do not recommend that students do this. There's actually another way that you can get the same result without having to remember this extra formula, and that's what I'm going to jump into now. So jumping back into our Desmos animation here, you can see that this green line, for example, here, this would be the linear approximation of the graph of sine of x around x equals 1. And again, you could do it around different points. This animation is already programmed to automatically adjust. But basically, you can see that we can always come up, again, assuming it's differentiable, which it is everywhere here, we can always come up with a linear approximation at every point. So there you go. That's kind of the idea. Now, the question I have is, what does this remind you of? It turns out that this is actually something else that you've already done before, even though you might not realize it. I'll give a pause for a second. You can also kind of see it in the name. I kind of gave it away here. This is the tangent line. In other words, the linearization of any function around a certain point is the equation of the tangent line of that function around that point. They're literally the same. Hopefully that makes sense. But you don't need, in my opinion, to remember this another entire formula because you actually already know how to find the equations of tangent lines to certain functions around certain points. That's why I recommend when you're trying to find linearizations, you just treat it as if you're finding the equation of the tangent line because that's what it actually is. Now think about how do you actually do that? Well, remember the whole idea when we're trying to find the equation of a tangent line, basically what we do at a certain point, I should say, basically what we do is we find the slope of the tangent line at that point, at the point of tangency. How do we do that? Well, we take the derivative of the function and plug in the point of tangency. That's what this is. So this right here, if you think about it, this is how you actually find the slope for the point slope form whenever you're trying to find the equations of tangent lines. And then again, what's the x value and y value of your coordinate? Well, the x value is literally A, the center, the x value of the point of tangency. And then the y value, think about how you find that. You just take that point of tangency, the x value, and plug it into the original function. So this entire thing, this entire linearization equation, a function of x that's a straight line, you can literally just think about that as point slope form for the equation of a tangent line that you would normally find the normal way. And in fact, that's what I recommend for students. They're the same thing fundamentally. And if you're curious, that's how I actually program the tangent line for this animation behind the scenes. This green line here, if I open this folder in Desmos, I'm actually just popping in the linearization equation. Or again, they're the same. So you could also think about it using point slope, the point slope form. But the Desmos is smart enough behind the scenes. If we specify a function f of x, Desmos is smart enough to calculate the derivative and also if we specify a certain a value, it's smart enough to calculate the derivative of the function at a certain a value if we plug this in. That's m, and then we can find the other points like this. So I'm just popping that in, and that's how Desmos is actually graphing this, and that's how it auto adjusts on this animation when I move it around. So that kind of begs the question, if the linearization is just the same thing as the equation of a tangent line, why do we have to learn a completely new topic? The answer to that is basically, even though they're the same, we use them differently. So, and this is where the approximation part in linear approximation comes in. So, you might ask, what exactly are we approximating? The answer is y values or outputs to the original function. What does this mean specifically? This means that if we're at a certain a value, in this case 1, what we can do, let me turn this on, is we can choose other values, other x values that are close by, and we can literally just plug in this x value to the linearization, and we'll get a certain y value. So that's what this green dot is. If you just take 1.5 and plug it into the equation of the tangent line that you found previously, or the linearization that you found previously, if you just plug it into that, you will get a y value out. And that's essentially what we're seeing here. This y value that you get out, you can see 1.111, that is the approximate y value. That's the y value that you get if you pretend that the linear approximation is the actual function around that point. So again, it's not perfect. There is as you can see, there is a gap here, but it's pretty good, and we'll talk about that a little bit more in detail. And then here you can always, and then here we're just calculating the exact same value, which is just 0. Or whoops, as I come back here, 0.997. That's the exact value. So this might beg the question: why do we even want to do this? Why don't we just find the exact value of the original function? Honestly, if you have a calculator or a computer, then yeah, that's actually the easiest. The reason linear approximations used to be useful, or honestly used to be popular, is because in a world before computers, it's actually a lot more work, and sometimes it's actually not even possible to calculate like sine of 1.5, for example, to like correctly. I mean, you can always come up with a decent approximation just by guessing, but like to actually calculate it out to a reasonable decimal place is actually kind of difficult. That's why this technique is in place, because it's actually very easy, or relatively easy by hand, to calculate the output for a linear equation. All you have to do, if you think about it, is multiply by one thing and add by another. That's it. You don't have to deal with any trig functions by hand. You don't have to deal with any crazy like exponents by hand. None of that stuff. It's actually pretty straightforward. So that's really the use case. We can approximate the y value. This is our approximation. That's the y value on the tangent line for a certain x value. and we can use it to approximate what the exact value would be. And again, there's always going to be an error in general. I guess accidentally they could match up exactly, but usually there will be an error. And that's kind of what this gap is. So as the test point gets further away in general, you can see that the gap between the actual y value and our approximation of the y value in general, as we get further away, is getting way worse. As we go way out further here, this is a terrible approximation at this point. This green line is nowhere, like this y value on the green curve on the tangent line is nowhere near the actual y value at that point. Why is that? Basically because our x test value is really far away from our a value. If we got a lot closer, so if we come in a lot closer though, and we get really close, so like if I test right around that center point, right around a equals 1, then you can see that they're almost the same, 0.891 versus 0.895. This is less than 0.5% error. Whereas when we went out here, you can see that we're talking about hundreds of percent worth of error here. So it's pretty significant. So that's basically the idea. At any given time, you can use the equation of the tangent line, and you can literally just plug in certain x values around the point of tangency into that equation, get the y values out, and then those y values, as long as your x value is pretty close to the point of tangency, they will be pretty good approximations, and you can actually quantify it with an actual percent error. If you calculate the difference and divide by the y value of the exact, you can actually put an exact number on it. But basically, as you get closer and closer, you can see that the percentage error is going to shrink and shrink. So that's the idea. These are just tangent lines, but we're using them for something differently. We're using them to approximate y values more easily with fewer calculations around a certain point of tangency. So there you go. Hopefully that all made sense. If you want to use the Desmos animation that we used in this video, be sure to check the link in the description. You can use the same one. It's actually pretty handy for your problems as you're working through linearizations. You can always check your work with the calculations that it is doing. All you have to do is plug in the original function, the point of tangency, and then the x value that you want to approximate it at, and it'll spit out the exact y value, the approximate y value, and the percent error, which is usually what they ask on these types of problems. So that can be pretty helpful, I think, as you're going through your homework problems and trying to double check your work. So hopefully that all makes sense. Be sure to pick that up, and I will catch you next time.